This is a podcast to outline the chi-squared distribution and its use for significance testing to be contrasted with the t-test information, and also to build on what you know about p-values and probability. So what is the chi-squared for? You may have come across it at school. Well, it's to measure discontinuous, categorical or bin data. And you put things in categories, so it's not continuous data. So a rule of thumb is it's when an observation is a word, not a number. So you could say, what sex are people? Well, they're male or female. What genotype, if we're thinking about Hardy-Weinberg, or if we're talking about injuries, we could say you've either got a broken ankle, a normal ankle, torn ligaments, sprained ankle, that type of thing. So basically what we do is we measure our data, and we have observed data, and then we compare it to what we would have expected if there was no difference, no significant effect of whatever the treatment is we're thinking about. So briefly, you've got to have one or more categories, independent observations, a sample size of at least 10, random sampling, use all the observations, and the expected frequency numbers should be at least 5. So how do we do this? Well, you make a hypothesis. Remember, this is about biology, not stats. We then calculate the expected frequencies, that is the frequencies we'd expect to see if there was no effect, and we usually do this in a table with observed frequencies, expected frequencies and chi-squared values, and we calculate the chi-squared value using this formula. So it's the observed value minus the expected value, you square that, you divide through by the expected values, and you add all those up, and that's the value, that's your chi-squared value. Then you determine your degrees of freedom, which, as we'll see in a minute, is rows minus 1 times columns minus 1, and then you look this up in a table, and you find for your degrees of freedom that you have and the level of significance that you're interested in, and that's going to be below 0.05 or below 0.01 or below 0.001, depending on how stringent you want to be. So you use that value and the degrees of freedom to find the critical value in the chi-squared distribution table, and then you compare the critical value in your chi-squared value, your calculated value, and if the critical value is greater than your calculated value, you don't reject the null hypothesis, so you conclude therefore that there's no effect. So here's an example of testing for proportions. So here's a horned lizard, and the hypothesis is that these animals that eat insects, they eat equal amounts of leafcutter, carpenter and black ants. The alternative hypothesis, if we reject the null hypothesis, is that the horned lizards eat more of one species than the others. So here's our observations. So we observe in 60 different tests that 25 leafcutter ants are eaten, 18 carpenter ants and 17 black ants. Now, in this simple example, if there was no effect, we have 60 observations, we would expect 20 of each to be an even amount of each type of ant to be eaten. And then we can easily calculate the observed minus the expected. So 25 minus 20 gives us an observed minus the expected of 5 for the leafcutter ants, and so on. You will observe that some of these values are negative, but when we square the observed minus the expected, we end up with a positive value, and then we divide the observed minus expected squared by the expected. So for the leafcutter ants, we divide 25 by 20, obtaining 1.25, and then to get the calculated chi-square value, we simply add up 1.25, 0.2 and 0.45, which gives us a chi-squared value, a calculated chi-squared value of 1.9. Degrees of freedom, we have 3 columns and we have only 1 row, so we ignore that. There are 3 columns, columns minus 1, 3 minus 1 gives us 2 degrees of freedom. Here's a chi-square distribution table. You can find them on the web or in statistics books. We have 2 degrees of freedom, and we're interested in a significance value of at least 0.05. So if we look that up, you can see that the critical value of chi-squared is 5.99. So the chi-squared statistic, the critical value is 5.99, and our calculated value of chi-squared is 1.9. Remember, if the critical value is greater than the chi-squared value, then we can't reject the null hypothesis, and clearly 5.9 is greater than 1.9, so we don't reject the null hypothesis. And what's the biology mean in that? Well, it means horned lizards don't discriminate between different species of ant. They basically eat the same amount of each. We can do multiple testing with chi-squared as well, and in this example we're going to think about the number of injuries that we get, different types of injuries we get in different sports. So we've got 3 different sports and we're going to have a number of injuries. We've got football, cricket, and rather stretching a point, ballroom dancing. So here's our observed data. We've got broken ankles, torn ligaments and severe chafing, and we've got football, cricket and ballroom dancing. You'll notice that these are our observed values, these 9 observed values. So this is our data, and we have 75 totals for football, cricket and ballroom dancing respectively, and we have 70 examples of broken ankles, 80 examples of torn ligaments and 75 examples of severe chafing. So this is this 70 is this column added up, this 75 is this row added up, and so on. And you'll observe as well that in total we have 225 observations. That's the total number of observations. It's slightly more difficult to calculate the expected values now. It's not so obvious. We use this formula. So the row times the column totals divided by the total. So this is a row, and this is a row, sorry, and this is the column, and this is the total number. So for example, let's do the calculation of the expected number of broken ankles in football from this data. So we've got 75 as the row, and we've got 70 as the column total, and 225 is the total overall. So 75 times 70 divided by 225 gives us 23.3 expected broken ankles in football. And we can follow that using the row and the column totals and the total number of values to calculate the expected values for each of the injuries for each of the sports. We can then do the observed minus the expected for each. That's comparing the first 2 tables, gives us this answer. We can square those as we did in the previous example, and then we divide the observed minus the expected through by the expected value, and that gives us these values. And then we simply add up these 9 values. If we add up these 9 values, the sum of the chi-squared values, we end up with 123. Now we calculate our degrees of freedom. Now we do have columns because we have more categories. So it's columns minus 1 times rows minus 1, 3 minus 1 times 3 minus 1, 2 times 2 gives us a total of 4 degrees of freedom. So let's be more stringent this time. Let's look in our chi-square distribution table, and let's assume we want a significance of at least 0.01, that is 1%. We have 4 degrees of freedom, so our chi-squared statistic is 13.28, 13.3. So we've chosen a significance level of 0.01, the critical value is 13.3, the calculated chi-squared is 1.23, the critical value is less than our chi-squared, calculated chi-squared, so we can reject the null hypothesis in this case. 13.28 is less than 124. So what we conclude from that is that there is a significant difference in the injuries occurring in different sports. Of course, it doesn't tell you where that injury is, which sport it is, or which injury it is. You would have to go in and look at that in more detail and use some other tests or some plots or some other analysis to find out specifically where that difference is. Chi-squared or t-test. Well, as we said right at the beginning, you use chi-squared if your outcome is categorical, so the colour of a flower, for example. You use a t-test if your outcome is continuous, such as height or weight, for example.